Okay, let's continue on with power factor correction. So what we have here is our circuit before we correct the power factor, so just the source along with the motor. Now after we correct the power factor, the circuit's going to look like this. We still have the source and the motor. By the way, this is still J86.7 ohms. I just had to squeeze it in. But to correct the power factor, we're going to put a capacitor in parallel with the impedance of the motor. So this is something I'll explain in more detail later, but when you correct the power factor and you add the capacitor, you always put it in parallel with the impedance that you're correcting the power factor for. Remember, this impedance that we figured out last video has a power factor of 1/2 lagging. So this capacitor is going to make the impedance have a power factor of 1, which means the angle, the theta z of the capacitor along with the motor will be 0 degrees. And we do this by equating the capacitor reactive power to the inductive reactive power, which we calculated to be 118.6. Now if you look back a couple of videos ago, we had this expression for Q, that Q is equal to voltage squared divided by X. So for QC, this would just be the voltage across the capacitor squared divided by the reactance of the capacitor. And you see, we know that QC is 118.6. Also, since we put the capacitor in parallel, we know the voltage across the capacitor is 117, since voltage is the same in parallel. So we can calculate the reactive, or the reactance, excuse me, XC, from just taking 117, the voltage across the capacitor squared, and dividing by the 118.6 VARs. Okay, that comes out to a reactance of 115.4 degrees, or excuse me, 0.4 ohms. And we know that reactance of a capacitor, okay, XC, is just equal to 1 over omega C. Also, I forgot to write it here, but it's in the previous video, that our source frequency is just in radians per second, 2 pi times 60. So you see, I can solve for the actual number of farads C that we need by just taking 1 over omega C. So if I plug in the 115 here, and then this is the 2 pi 60, it comes out that the capacitor that we need to put in parallel with that motor to make the power factor equal to 1 is 23 microfarads. Okay? Now, let's see what effect having this capacitor has on, or by adding this power factor correction capacitor, let's see what effect it has on the current that's flowing in the line here. Okay, this is the line current. It's the current flowing between the source and the impedance. So here we already calculated that this I before, and we'll write it over here right above, that the I flowing, oops, put it right here, the I flowing through the line was 1.17 amps. Okay, now to get the current that's flowing in the line afterwards, we could find the Z equivalent of this whole impedance here, the impedance of the motor with the capacitor, and then divide that into the source voltage, and that would give us the source current. But instead of doing that, let's use the relationship between apparent power and current, right? That for an impedance, apparent power is just equal to V times I. Okay, so we know the V across the impedance is the source voltage because everything's in parallel, so we got 117 across the capacitor and the impedance of the motor. And the apparent power, once the power factor is corrected, the apparent power is just equal to P average. Okay, so you see this is after. Okay, after the power factor is corrected, because we made the angle of the power triangle 0, the hypotenuse, the apparent power, equals the adjacent side p average. So this is equal to I if we go ahead and divide by V. See, this is only true. P average divided by V is current when you have the power factor corrected. Okay, if not, then you have to use apparent power. So if you go ahead and calculate this, you'll get that we have a P average of 68.5 and the voltage is 117. So that gives us a current of 0.585, 0.5 amps. So you see that's what's flowing in the line between the source and where the impedance is after the power factor has been corrected. Okay, so you see once the power factor has been corrected, the current in the circuit, in the line between where the source is and where the impedance is, has gone down. In fact, it's gone down by a factor of 2 here. See, it went from 1.17 amps down to 0.585 amps. And what that means is that you have less loss in your lines. You know, each line has some resistance, and the amount of watts, the amount of power that's lost in the line is the current squared times the resistance of the line. So you see, when you cut in half the current flowing in the line, well, you reduce the power lost in the line by a factor of 4. Or another way to put it is that if you don't correct the power factor, you've got 4 times the amount of loss in the line than you would if you did correct the power factor. And you see, this is important, and this is the main reason why correcting the power factor is done, because the power company, we go back to our previous circuit here, you know, this source could represent a power company like PG&E, and you know, this motor you know, could represent like a motor in a piece of equipment at a manufacturing place, let's say. Well, if there's a manufacturing firm with, you know, lots of equipment and motors, and they don't correct their power factor, they're costing the energy company, the power company, money, because they're creating more loss in the line than what's you know, what's possible. You know, if they correct the power factor, they can reduce it. So that becomes a cost to the power company. Now, another important aspect of power factor correction is realizing that when the power factor is corrected, you actually do not affect motor performance. Okay, so if we go back here, and well, nope, we gotta go back to the previous page, sorry about that. Yeah, if we look at this circuit here, and we want to see, well, is the performance of our motor changed after we correct the power factor? And the way to answer that question is by looking at the current through the motor. Okay, the current through the motor is what creates the magnetic field that you know, produces the torque inside a motor. So if the current is maintained through a motor, its performance will be maintained. So if you look here, before the power factor is corrected, there's 1.17 amps flowing through the motor, and that comes from the 117 volts divided by this impedance 50 plus J86.7, as we did in the previous video. Well, look, after the power factor is corrected, you're still going to have the same amount of current through the motor, because it still has 117 volts across it, and the impedance of the motor hasn't changed. It's still 50 plus J86.7. You know, the Z equivalent, you know, the total impedance of the capacitor in parallel with the motor, well, you know, that's different, but the impedance of the motor itself has remained the same. Okay, only the Z equivalent's been altered by putting the capacitor there. So the answer to the question about motor performance is that the current before, okay, and this is motor current. Okay, so the current through the motor before the power factor is corrected is identical to the the current through the motor after the power factor is corrected. Okay, so that raises the question of, well, how can that be? Because if this current through the motor is the same as it was over here, and yet the current from the source, right, the current between the source and where our capacitor and motor are has decreased, well, how could this current be maintained? And the answer to that is that the capacitor is supplying the balance of the current. So the capacitor makes up for the decrease in source current. In a real practical type of scenario, going back to the sources like a power company and the motors like a piece of equipment, say at a manufacturing firm, well, these capacitors that correct the power factor, they're located at the firm, at the manufacturing plant. So you'll hear EEs and engineers refer to this capacitor as supplying Q locally, because that's effectively what's happening, is that when you make the power factor equal to 1 and you make the angle equal to 0, you're eliminating the Q, the exchange between the source and the motor. So you see here, before we correct the power factor, the Q is going back and forth between the source and the motor. Here, once we correct the power factor, there's no longer an exchange of power between the source and the motor, but now there's an exchange between the motor and the capacitor. So there's a Q in both of these circuits. It's just that the Q here is between the source and the motor, and the Q here is between the capacitor and the motor. And not having the Q in the line is what reduces the current in the line, which again reduces your line loss. Okay, one more thing in this video, and then we'll do one other example in the next video to finish up power factor correction. But the last thing is why you do not want to put the power factor correction capacitor in series with the motor. Okay, so why do not use series power factor correction cap? Okay, abbreviated. And the easiest way to answer this question is to actually do it and see what happens. So we're going to take the same source of 117 0° volts. Okay, the same motor. So this is 50 ohms, J 86.7 ohms. And then the capacitor. Okay, so to correct the power factor in series, well, or by using a series power factor correction capacitor, well, to get what XC is, okay, because remember, once we have XC, we can get the capacitor value, right? Because that's just going to be C equal to 1 over omega XC, like we did previously. Again, omega here is just 2 pi 60. Well, this is just like a series bandpass filter, that when you correct the power factor and make the angle 0, remembering that the angle of the power triangle is the same angle as theta z, well, just like you learned with bandpass filters at the resonant frequency, when the impedance of these storage elements are the same, but opposite sign. So here, when the capacitor has an XC that matches the XL of the inductor, okay, or the impedance of the capacitor is the same magnitude but opposite or negative phase. So, if we got plus J86.7, well, if the capacitor has impedance minus J86.7, well, they cancel out, and you're just left with the resistance, which has a theta z of 0°, and that's what your degrees of that's what your theta of your power triangle would equal. making the power factor equal to 1. So you see, when you put the capacitor in series to correct the power factor, finding the capacitor value is easier than what we had in the parallel case, because in the series case the reactances are just the same. But if you go back and look at when we solved the parallel case, you can see that the correction power factor, or excuse me, the reactance of the capacitor to correct the power factor, was a different amount of ohms than what the inductor is. See, the 115.4 compared to the 86.7. Alright, but this is why you don't correct the power factor with a series capacitor, because when the capacitor and inductor reactances cancel out, we'll look at what current's going to flow in the line here. Remember, this is the line current right here between the source and where the capacitor and the motor are. Well, look, that I is going to be equal to the source voltage of 117 divided by 50 ohms, just the resistance. So now look at your current. Your current's going to be more than 2 amps. In this case, 2.34 amps. So your current is actually more, your source current or line current is actually more than what we had when we started. See, before we corrected the power factor, it was 1.17. If we correct the power factor putting the capacitor in series, well, our current increases. And if our current increases, well, guess what? The line loss is going to increase. In fact, this current here doubled, right? It went up by a factor of 2, times 2 increase. Well, the power lost in the line would shoot up by a factor of 4, quadruple. So that's why, or this is why, you don't put the correction capacitor in series, because you actually will increase line loss, and the whole main purpose of correcting the power factor is to decrease line loss.